Hello and welcome to this screencast. This video tutorial, I will show you how to work with Y-GEO FEMDEM code and Y-GUI, the graphical user interface. Just to give you a brief overview of Y-GUI and Y-GEO. Y-GEO is the engine, is the combined discrete finite element, or the FEMDEM engine that we use for running our models, while Y-GUI is the graphical user interface. So basically you build your models in Y-GUI, export it and run it with Y-GEO. Let me start by giving you an overview of Y-GUI, which is the graphical user interface for FEMDEM. As you see here, Y-GUI is organized into a couple of menu items as well as a number of tabbed pages. Basically, whatever you do is in these tabs, and these tabs are organized in the same way as the internal databases of Y-GEO FEMDEM code. You do most of the graphical stuff in the graphics page, where you assign properties to the elements, or assign boundary conditions to the nodes, or initial conditions to the nodes, and so on and so forth. And of course you visualize, you can zoom in and out and so on. The way to start a model is to first generate a mesh, that is to discretize your domain. Y-GUI itself doesn't have any mesh generation feature, so you would have to generate your mesh in another program. At this point you can import meshes from either Phase 2 from Rock Science or Abacus, so .fea of Phase 2 formats and .imp of Abacus. If you have other programs that you would like to use for generating your mesh, you can either easily create a script or a program that will translate it to either of these two formats, or the Y input format, which is the generic Y-GEO input file format, or you can contact me and I will at some point create an import filter for you. So in this tutorial I would like to show you how to set up a model of a uniaxial compressive strength test, which is a standard rock mechanics test. In this test, as you see on the screen, you would have let me just turn off these things so you will see the mesh better. You will have your rock specimen, which in this case of the 2D FEMDEM model will be a rectangle, and two loading platens by which we would apply the forces to the rock and will break it eventually. So the first thing to do after you have generated your mesh, I have already generated my mesh, so I will go to File, Import Mesh, select triaxial or biaxial or uniaxial, it doesn't matter, select the mesh and import it. So turn off the mesh here, so when I turn on the mesh on this right side you will see the mesh. If you see Y-GUI, on the left you have the graphics page, on the right you have the messages box where it tells you what you did. So for instance, the last thing that I did was to import the mesh at this location. This mesh contained 16,232 elements and 8,282 nodes. As you see here, it gives you a snap distance. This is when you select nodes, and you can change it with these comments given here. We will look at that later. In the graphics page you can easily zoom in and out by using the wheel button of your mouse, or using the zoom in and zoom out options that you have here, and you can of course zoom to extents or refresh your view. So I will start by going to the first tab here, which is the control database. In this one, in the control database tab page, you have the general control parameters. These are the general parameters that control your simulation. It starts with the maximum number of time steps. As you may know, FEMDEM, Y-GEO FEMDEM uses an explicit time integration scheme and is fully dynamic, so you will have to specify the time step size and the number of time steps that will give you the duration of your simulation. In this case I have assigned 1,000,000 time steps with a time step size of 5e⁻⁶. As you see here, there are no units given here. That is because you can use any set of compatible units. So if for instance you want to use SI, then you would have to take care of your units and make sure that the time step size is given in seconds. In this case, since my rock specimen is fairly small, it's almost 5 centimeters, as you see here. It is almost 5 centimeters by 10 centimeters. When you roll your mouse over here, in the bottom left corner here, this corner here, you would see the coordinates of the cursor. So since my model is fairly small, I decided not to use SI units, because if I use SI, then the width of my specimen will be 0.05 meters, and in each time step the amount of strain or deformation that you calculate will be really small, and I'm afraid that I will have rounding errors. So instead of using meters as the units of length, I've used millimeters, and instead of using seconds, I've used milliseconds, and later on I will tell you that instead of using kilograms, as is used in SI to get into newtons, I've used micrograms. So let's go back to the control database page. So I've decided that the time step of 5e to the minus 6 is good for this one. The way you can find the time step is a little bit by experience. You want to have a sufficiently small time step to ensure that your time integration scheme will be stable, and at the same time you want to have a big enough time step size to have manageable run times. Okay, so there is always a trade-off between runtime and of course stability of your integration scheme. Output frequency defines the number at which, the frequency at which you will export output files. In this case, let's say I want to have outputs printed at every 5,000 time steps. I don't want to assign any gravity to this model. Gravity doesn't really play an important role here. These maximum coordinates, force, velocity, and stresses, they are just used for the visualization program that comes with Y-GEO. At this point, my mesh is about 75 millimeters in the biggest direction, so I assign 76 to have everything in center. A maximum velocity of 2 meters per second or 2 millimeters per second, and a maximum stress of 50 MPa. You don't have to worry about the other stuff. The only other things that you may have to worry about is the maximum number of elements and nodes. These two parameters are used when you import a mesh in Y-GEO. The program will generate so-called four-noded joint elements on the edges of your finite elements. So basically, on the edge of each two finite elements, you will have a joint. Therefore, the nodes are duplicated, the nodes of your model, and here you want to assign a relatively big number that will ensure that you will have enough spaces for the array. So it's just how the arrays are initialized. You want to have a big number for these, but not so big, because if you assign a very big value, then the arrays will become really huge, and the initialization of the program will take a long time, and also your simulation generally becomes very slow. So you want to have a relatively big number, but not as big as to make your things very slow. In this case, for instance, we have about 8,000 nodes, as we see here, and 16,000 elements, so 100,000 should be a good estimate of these values. Then let's move to interaction. In interaction, you define all the parameters that are used for the contact interaction and, of course, contact detection of the code. The two important parameters that you have to take care of here is the maximum number of contacting couples. Each two finite elements that could potentially be in contact are defined, or they do define a contacting couple. So here again, you want to have a relatively big number of contacting couples, but again not too big. So in this case, 300,000 should be enough. The other important thing that you have to define is the size of buffer. This is used in the contact detection, and as a rule of thumb, you want it to be about 1/4 or 1/5 of the average element size. In this case, I use a uniform mesh size, relatively uniform mesh size of 0.8 millimeters for my rock specimen. So divide that by 5, I get 0.16 millimeters, and that will be a good size of buffer. You don't want to have a very small buffer size, because then you might lose or miss the contacts of the two elements, and you don't want to have a very big value because it makes the contact detection really slow. Hello, well, the next thing is to go to the properties page and define the properties, the material properties that will be assigned to the elements. As we see here, we have the rock specimen, which in this case I would like to create a heterogeneous rock specimen consisting of two different properties or two different materials, and also the loading patterns. So in total we will have 3 property sets. I will start by putting in the values for steel. A typical Young's modulus of a steel will be 191 gigapascals. 0.29 will be a good Poisson's ratio. I will also assign a small friction value for the contact between the loading platens and the rock specimen, and this is the density of the rock. Viscose damping. For viscose damping, you want to critically damp your elements. A typical value that you can use as a rule of thumb will be 2 times the average element size in that property set times the square root of elastic modulus or Young's modulus times density. So I've calculated these for the loading platens. It will be 2.9 e to the 8. Contact penalty, a value around the value of elastic modulus will be nice, the same as tangential penalty. So then you can select the color, whatever color you would prefer for this property set, and click on Add Property Set. And on the right side you will see a table that summarizes your values. Then I will put in the values for the rock specimen. Let's say that the average rock, which consists of 90% of rock specimen, these are just assumptions I'm making on the go, has an elastic modulus or Young's modulus of 53 GPa, a Poisson's ratio of 0.23, a friction coefficient of 1.27. Remember that this friction coefficient is the tangent of the friction angle, and 2650 will be a good density. Here, as I said before, there are no units, but the beauty of using millimeters, milliseconds, and micrograms is that most of the variables will still have the same values as in SI. That includes all the things that are that have the units of stress, for instance Young's modulus, or the ones that have the units of density. Okay. Viscose damping for these ones will be 5.9 e to the 6. For tangential and contact penalty, again I will use values similar to the Young's modulus of elasticity, 53. I will select a different color for these ones, let's say dark green. The last property set will be another material in this rock. Let's assume that these are biotite grains that consist of about 10% of this rock. A good guess for the Young's modulus will be this value that I entered. These values were taken from literature. I'll keep the friction the same. Enter the density, the viscose damping, and then the penalties again related to the Young's modulus. At this point I'm keeping both of these penalties the same. I will choose a different color for these ones. So now I have these 3 property sets that I can start to assign to my mesh. So I go to the graphics page again. Here on the right side I will click on the PR icon, which is for assigning property sets to the elements. I can draw a rectangle around the elements that I want to select, and at this point you will see that I've also selected the 2 platens. To deselect them, I will hold down the control button and click on those 2 elements, and as you see they are not highlighted anymore and they're not selected. I would like to randomly assign the 2 property sets that I had, property set 1 and property set 2, with these 2 colors to the mesh. To do that, I will go to the heterogeneity page. Okay, say 90% will be property 1 and 10% will be that other property too. We'll go back to the graphics page, right click, assign property, random assignment. I will turn off the mesh by clicking on this checkbox here, and this is the random assignment of properties based on 90 and 10% distribution. If I right click property random assignment, each of these will end up or result in a different realization of random material assignments. Okay, let's assume I'm happy with this one. As you see, PR is still active, which means that I'm still selecting elements and assigning properties to them. Once I'm happy, I would right click and click on done. So this is done now. Now I can assign the properties to the two loading platens. I will select them, right click, property, and from this drop down menu I will select 0, which stands for the rock specimen, and done. Turn off the mesh. So these ones have the color of the property set 0, which is the steel platen, and here I have the rock specimen. The next thing is to go. One thing to always remember when you're working with Y-GUI is to save your work from time to time. To do so, you can go to File, Save As, and select with whatever name you like to give it. So I'll call it UCS. Save. Okay. And of course, it will give you some error messages at this point because you haven't selected everything, but nonetheless, it will still export your file. As you see here, this is ucs.txt that it exported, and if I open that in any text editor, you will see that it does have some information, and it has the information assigned to that. Looking at these input files is something else, and I don't want to go into the details of that at this point. So the next thing after you have selected and assigned your properties to the elements is to define the joint properties. These joint properties will be used for in the fracture model of the code. Basically, on the edge of two neighboring finite elements, and a joint element will be inserted. These joint elements, since they're located on the edges, will have 4 nodes. Here I would like to create 2 joint sets. One of them is for the average rock and one of them for the biotite grains. I would start by defining the friction value, the same as before, 1.27, cohesion of 26 MPa, and again this is the same in SI as in the millimeter, millisecond, and microgram set of units that I'm using at this point. I will leave shear strength as 0. Here you have 2 options. You can either define a constant value of shear strength for your model, which will be used for the elements throughout the simulation, or you can define friction and cohesion, in which case a more Coulomb type friction, more Coulomb type failure criterion will be used, which is more realistic for most rock mechanics problems. So I'll leave the shear strength as 0. A tensile strength of 5 MPa is right for me. It's the value I wanted, and this is the value that I've assigned for mode 1 fracture energy, and I'll use double of that for mode 2. Fracture energies are the only 2 things that will change when you don't use SI units. In this case, the actual SI value is 239 Newton over meters or Joule over meters squared. After I'm done with these ones, and of course I have to set a right fracture penalty, which is similar to the Young's modulus, I will click on Add Joint Set, and now I will define the values that I would like to use for the biotite. The only thing I would change is I would decrease the tensile strength slightly, and the same with mode 1 and mode 2 fracture energies. Once I'm done with these ones, and of course once I also update the fracture penalty, I will select Add Joint Sets. So at this point you would see that I have added 2 joint sets. Now I have to define what is the relationship between these joint sets and property sets. To do that, I will move to the meshing page. Here I will add a meshing set with refinement 0 for property 0. It means that don't do anything for property 0 which is associated to the steel, but I want to mesh together, or I want to introduce joints between properties 1 and 2, which are for my rock specimen. So here I will say property set 1, property set 2. These are the property sets that you defined in the properties tab page. Okay, and I want to mesh them. In order to mesh them, I have to say 3 here. This is just a Y-GEO code. This one means that when you initialize your simulation, it will loop over the elements and duplicate the nodes and introduce joint elements between them, which means that you enable fracturing in the model. Once you have these ones, you have to say what goes within property set 1, what goes within property set 2, which is the biotite, and what goes on the interfaces between them. Okay, so I will add a couple of these sets. Let's say between 0 and 0, which is the still, it's not really used, but as a rule of thumb, I'll just do it just to make sure the program doesn't crash. Then between 1 and 1, which is for my rock, I would say 0, because the 0 was the average rock properties in the joints that I wanted to have. So here, these two first columns refer to the property set IDs that you define in the properties tab page, while the last column refers to the joint property sets that you had here in the joints page. So between 2 and 2, which is the biotite, I wanted to have the weaker joints. And between 1 and 2, it's up to you if you want to use the properties. Oh, sorry, this should be 1 here. Between 1 and 2, you can select whatever you want to have. I would say I will leave it as the average rock. Again, just to be sure, I will export. This is again one of the other ways. You can either do export from here or from file save as. Okay, so I've exported these ones at this point. So the next stage is to go to the boundary conditions page, define the boundary conditions that you want to apply to the model, and apply it here. So I want to move the two platens towards each other with a fixed velocity in y direction. Okay, to do that, I'll go back to the boundary conditions page. We'll say velocity in x, let's leave it as 0. Velocity in y, let's give a positive value of 0.125 with a red color so that I can easily see that. Add. Then I will have another property set, again 0 in x direction, negative value in y direction. Add that, which is a different color. And regardless of whatever you want to do, even if you don't want any boundary conditions assigned to the specific nodes, you still need to have to assign boundary conditions to all of the nodes. So basically all of your nodes in your domain should have a boundary condition assigned to them. So that's what I would call a dummy boundary condition that we use either force or velocity as 0. So basically it doesn't do anything. It just adds 0 force at the end of each simulation loop, but it still has to be there. And as you notice, for properties at 0 and 1, I selected force 0 for these two. It would be a better idea to select velocity, so just to make sure that the platens are not moving in the x direction. And as you see, it's fairly simple to update these ones. You just have to select whatever property set you want, and these fields here will be updated. So let's say 0, and I want to update that with 3. Once you're done, it's not updated here. You have to click on update current boundary condition set, and as you see, it is updated here. The same with property 1. I would select velocity, update. So this is updated as well. You can have the same option in joints and in properties. So basically you can select, and as you see, these will be updated. The next step after you have defined all the boundary conditions is obviously to go to the graphics page and assign those boundary conditions to the nodes. Remember that all nodes of your simulation should have a boundary condition set assigned to them, no matter if the boundary condition is actually doing anything, like our boundary conditions 0 and 1, which apply velocities to the nodes, or they don't, like the boundary condition 3, which doesn't actually do anything. So go to the graphics page and click on the icon called PC, which is for assigning boundary conditions to the node. What I would do, I would assign the dummy boundary condition, or boundary condition number 3, to all the nodes. So something like this. Right click, assign boundary condition. I select the third one. Done. As you see here, with the color that you defined here, these nodes will be highlighted. At this point it's so dense so you won't see it, but if I zoom in, you will see that all of the nodes now have the color of the third boundary condition set. So I zoom out. Now what I want to do, I have to assign the velocities to the nodes. So let's select the nodes of the top triangle. Okay, so I have selected these ones should have the second set here. So right click, assign boundary condition 1, and as you see the arrows point downward, which show the velocity going down. And I'll do the same thing for these ones. As you see, at the time I'm selecting nodes, on the right side it tells me how many nodes I've selected. It doesn't tell you which exact node, which you can visually see, but at least it gives you an idea of how many nodes you have selected. So at this point I've selected the 3 nodes of the bottom platen, and I'll assign boundary condition 0 to them. Right click, done. So at this point I've assigned all the boundary conditions to my nodes. As you noticed, especially for the dummy boundary conditions set, which is this olive color over here, it becomes a little bit messy for the visualization. So one option you have here is to go to the boundary conditions tab page and turn off that property set. As you see here, like that's turned off, and it's much nicer. You still have all the boundary conditions here, but not with the ones that are distracting. You can also turn on and off all the boundary conditions by selecting on these on the checkbox here. So that's it for the boundary conditions. So now that you've defined all the fields in the control database, interaction, you've defined all your property sets and assigned it to the mesh, you've specified all the joint properties and specified how those joints and properties are related to each other, specified the boundary conditions and applied those to the mesh, you're more or less done. You've done all the basic steps of creating a Y-GEO FEMDEM input file. Of course, you have to import from time to time. The only last things that you might want to do is to apply initial conditions if you had them. So to do that, you will just click on V0, select the nodes you want, just the same way as for boundary conditions. Right click on initial conditions and assign initial velocities. You will specify the Vx and Vy. Okay. And the last thing is perhaps you want to have some history points. These history points are used to record the velocities or stresses at given points. For instance, when we have the loading platens, these 2 platens here, we want to record what are the nodal forces on those platens. So the way you would do it is to right click, define output history point. Here you see you have the options for velocities, forces, and stresses, of course, and of course the total kinetic energy in the system. Stresses and velocities are evaluated inside the finite elements, while forces are evaluated on the nodes. So when you define stresses or velocities, you just have to click approximately where you want to have them, and the program will find the closest cell or the element in which they fall in. When you want to define forces, on the other hand, you have to specify the exact location of the nodes, otherwise you will get 0 forces. So let's assume that I want to record the forces on the top platen, and I want to record vertical forces. So I would click on force Fy. Okay, as you see here, a window will pop up that allows you to define the exact coordinates of the points, and as you see when I'm moving my mouse, the cursor, the coordinates in the box are updated. At this point, of course, it will be very difficult to click the exact locations of these 3 nodes. So what I would do, I'll just click on their approximate locations, 1, 2, 3, and as you see these points are added, then right click, done. Then you can go to the output history page, and here you have the option to change the coordinates of these points and also to change their type. As you see, their type is 19, which stands for a nodal force Y. Now if you want to get the exact coordinates, you can either look at the mesh generation software or just look here. If for instance I zoom in a little bit here, okay, if you select this checkbox here which says node number, okay, and then you click on the node, it tells you which node you selected, it highlights it as you see here, and On the messages window, it tells you the node number and also its coordinates. So this is very handy. You can use these coordinates in the other page. For instance, so this one was -30. So I'll get rid of all the unnecessary parts, and 53.805. This one again, it was 30 and 53.805. And for the top one, if I select this node here, it is at 0 and 75. So I would update this one 0 and 75. That's about it. The only thing that you may have to care about is the output history accuracy. I always change that to 0. By changing that to 0, it means that you're outputting the values for each single time step. Otherwise, it may not output for every time step, because it will look at the value that you define here as the difference between the two consecutive values. So as a rule of thumb, I always change that to 0 in order to get all the values. Okay, so now that I'm done with these, as you see here, those points, or the red dots here, were updated, and they fall exactly on the nodes. If, for instance, I turn off the show BC, you see that this output history file is exactly located at the node that I wanted. Okay, so let's say this is enough for me at this point. If you want to record like velocities or stresses at the center of your disk, it's very easy. As I said, just right click, define output history point, and record those. Now that I'm happy, I'll export the file, and now you're ready to run your file. You can just double click on the input file that you generated, which is ucs.y. If you have installed Y-GEO FEMDEM code, you can just double click on it, or just like any other Windows program, you can right click on it and define the executable, which I sometimes do, or run it under Linux, which I mostly do. So now that you've exported your input file and are running it with whichever method you choose to, if everything goes right, it goes fine, and you have no errors in your input file, you should be able to see your output. You will get two sorts of output files. One of them is the so-called .ym files, as I'm highlighting here. These are the visual output files, and you also get the .yh with a number file. These refer to the output history points that you defined. If you remember, in the output history we have output history 0, 1, and 2. So whatever you get, like YH0 refers to your output point 0, which was the force at this point here. So let's first look at the visual history point, the visual output. So if you double click on the ym file, you will see that the OpenGL window, which is for the post-processing, will open up. Here you can plot your output at a given time step. So I can plot the output at time step 0. At this point, the default is showing sigma yy, or the vertical stresses. Okay, and as you see, everything is green, which corresponds to 0 vertical stresses. If I plot the second time step, you see that the colors have slightly changed, and as you see, the specimen is getting loaded, and it's experiencing some compressive stresses. You can change some of the visual settings here. On clicking the settings, you can change the line thickness, line colors. You can change what you're showing. At this point, it's showing cracks and fillings. At this point, we have no cracks, so it won't show anything, but down the road, if you get cracks, it will show it with black lines as well. You can also change what you're plotting here. You can plot sigma xx, yy, xy, and velocities. Here you can also change the magnification. This is just a value by which your output will be multiplied in each single element. So if, for instance, I put 5 here, you will get more, you will get stronger colors basically. So something like this. So you get more red, which means higher stresses. Of course, it's just changing the output, not changing the actual values. And also transform in X, Y directions or scale if you want. So on, you can also animate by clicking on animate and clicking on the input file. It shows the animation of your simulation. At this point I only have 2 output points because I've just started running the model, but if you have the whole thing, it will show you an animation of the entire output. The frequency at which these outputs are printed out is given on the control database, the output frequency. It's different from what you find in the output history points. Okay. And the last thing to remember is that you always need this file, which is called mip.my or mip.my. This is just the defaults of how that OpenGL window should look like. So if the program couldn't locate this file in the folder that you're running the simulations, it may not, the OpenGL window may not show up. So you have to copy this file to each folder that you're running the simulation inside, and this file is located in the installation folder of Y-GEO. The other type of output are the output history points, as I mentioned. These are simple text files, so if you open those with any text editor, there will be all of these output files will have the same format. They are a 2-column file. The first column is time steps, so as you see, these are multiples of the time step size. The time step size was 5e to the minus 6, so that's the first output recording, and these are, for instance, vertical forces. And as you see here, you can easily import these in any spreadsheet program like Excel or OpenOffice or whatever program of your choices and post-process them. Just one last thing, if you ever have any output that doesn't look right or your model is not putting any output, you have to diagnose your input file. One of the most common problems that you may have is a time step size that is very big and causes instability in the simulation. But it's only with practice that you will gain knowledge on how to fix the problems in your input file. That's it for this tutorial. I hope you enjoyed it, and if you have any questions, just let me know, and good luck with using FEMDEM. Thank you. Bye.